This meeting is being recorded.
Sorry, I just forgot to record it. And for this talk, in the following 40 minutes, I'd like to demonstrate you my research statement. That is, artificial intelligence can enable and improve advanced text production and accessible interaction with pictures. In addition, new metrics for text entry enable the evaluation of advanced capabilities. And specifically in my work, I built intelligent text input methods with machine learning techniques to understand the writer's intention. And I apply user-centered design methods to explore intuitive ways for accessible communication with pictures. And finally, I derive metrics and models to evaluate those novel techniques and find insights. So today, I'm going to focus the talk on 3 domains of my efforts towards human-like communication. The first one is for text production. I will introduce 2 projects that utilize the language context to understand the users when they are typing or editing the text. And the second one is for non-textual information, such as emojis and GIFs. I will present 2 accessibility systems that enable blind or low vision users to naturally communicate with this information. And the last one is about the models and metrics for evaluating text communication systems. I will talk about a text entry evaluation model and how to theoretically incorporate the speed and accuracy into a single performance metric. So we will start from the text production. As I mentioned before, incorporating context is a key for computers to understand us. But how can we achieve that? Let's revisit the email example. Anyone knows English will understand there's a typo. And we do know that there are algorithms that are able to understand our language pretty well. For example, with the recent advancement in deep learning algorithms, computers are doing surprisingly well in language-related tasks. This table shows the machine translation performance from English to German, and we can see that some of the model even surpass the human performance. So what we need is to find a proper way utilizing the power of those models and to build intelligent communication systems. Jake, if you don't mind, can you help me admitting people from the waiting room? Thanks. So one such system I built is called phraseflow. Phraseflow is a keyboard that corrects the text in phrase level and by incorporating the surrounding context. Many previous research focused on making autocorrection algorithm more accurate. But the reason of having those funny typos is not the algorithm. The problem lies in the interaction side. The current autocorrection operates on word level. Once we finish a word, like be said, we press a space key, and that word is corrected and fixed. No matter what text you type later, the word won't change. Here is a demo of the word level autocorrection. When space is pressed, the word love is fixed. So even the final sentence should be, I live in New York. The keyboard cannot fix it. So I say, why cannot we delay the correction? In phrase level correction, the keyboard could also correct previous typed words if it finds the later context is helpful. So when you press space, be said is no longer fixed and can be corrected to best with the context regards. Here is a demo of phrase level correction. The word love is not fixed, even space is tapped. So when the keyboard sees New York, it can correct love to live. Here is another example of the word level correction on a long word communication, but I accidentally press a space within the word, which leads to 2 errors. With phraseflow, it is able to consider the context on both sides and successfully correct it to communication. So because phraseflow utilizes more context, it is smarter than the word level correction and could deal with different types of errors. For example, wrong word or typos that require later context, and also space-related errors, such as pressing space accidentally within a word. So some of you might wonder how to implement such a phrase level correction. Well, general autocorrection algorithm will use a state machine called Finite State Transducer, or FST, to correct the text. An FST contains two elements, the states represented in circle here, and the transitions. When the key is pressed, the FST will transit from the initial state to a new state, and it will continue doing so until the user finishes typing and press space. When space is pressed, the word level correction will execute the autocorrection and reset all the states and restart the whole process from the beginning. So when you start the next word, all previous states are lost. To make it into freeze level, we disable the reset transition and instead assign a new state to the space press. And in this way, the whole transducer is aware of all the previous states when new context comes and could make corresponding autocorrections based on the whole history. When we run simulations experiments on a computer, we found the freeze flow was able to reduce 16% of the error rate than the current word level correction. And the final prototype was evaluated in a lab study where people used both commercial keyboard and freeze flow for text entry. And we found that people had 19% less error rate when using freeze flow. And furthermore, we conducted a longitudinal study with 42 people where we installed the keyboard on their phone and let them use it for a week. And after the period, we found that over 78% of the users like the keyboard and would like to continue using it on their phones. So freeze flow focuses on the text entry part. It uses the later context to improve the input accuracy. But text production actually contains two parts, how you enter the text and how you edit it. If you want to edit something that's already there, like change a word, how can we make that more efficient? Suppose you are messaging to a friend to bring some coffee, but later on you decide maybe tea is better. So now you want to change coffee to tea. And what will you do if you are typing on your phone? Well, there will be a series of commands, right? You move the cursor to coffee and you delete it, and then you retype the word tea, and maybe you move the cursor back. But if you are talking with the person face to face, we can just specify the correction. For example, we can just say, some coffee, please. Oh, sorry, tea. The correction is done in one step because the other person understands what our intention is. So can we map something like this human-like interaction on our smartphone? The current scheme of text correction is to locate the error first, and then type the correction. However, if we can reverse the order, if we type the correction first and let the computer figure out how to apply the correction, then we don't need the cursor anymore. And that is type then correct. It's a novel correction concept implemented with 3 interactions. To make a correction, the user just needs to type the correct word and apply the correction with different interactions such as dragging, throwing, or pressing a button. I'm going to show you the demo of each of them. The first one is called drag and drop. This is a baseline interaction for introducing more innovative techniques. So after the user types the correction, it simply allows the user to drag the correction onto the error text to make a correction, or drag onto a space to make an insertion. And we say, okay, this looks cool, but it still requires the user to precisely move their fingers, which can be time consuming. So we made the second interaction, drag and throw, to speed up. After typing the correction, you drag the correction and throw it to the direction of the error text. And the algorithm will figure out what text is likely to be changed given the correction. And the last interaction is called magic key. And for magic key, there's no dragging at all. What you do is simply press the button on the left of the space key after typing the correction, and the algorithm will figure out what to correct, and you press the key again to confirm it. And with all these interactions, editing is just like typing new text because the device understands your intentions. And this seems like a magic. So how do we implement this? The intelligent interactions need to locate the errors given a correction. And to do this, we train a neural network model, which has two parts, an encoder and a decoder. We feed the correction and the typed text into the encoder. Here, the example is thanks the reply, and the correction is 4. And the decoder will output the correct version of the text. After the training, we have the model, and we plug it into the keyboard, and we conducted a user study to see how well it performed. And we found that indeed the intelligent interactions were faster. Basically, we asked the participants to compose a message and then correct the errors using different interactions. On average, it took around 6 seconds to correct a single error with the cursor. But drag and throw and magic key were faster. And we also evaluated the success rate. Drag and throw was a bit lower because sometimes the throw gesture can be hard to perform or there might be multiple errors around the place. But magic key, on the other hand, is 97%. The button provides a fine control on what to correct. And here are some further impacts of the project. The concept of typed and correct has since been adopted by many researchers from Stony Brook, Tsinghua University, Google to improve the correction interaction in different modalities such as touch typing and voice typing. Okay, so far I've introduced phrase flow, a phrase level text input system, and typed and correct, a novel correction concept. And I hope by now I've successfully demonstrated how we can design human-like communication for text entry to make the device understand our intentions and what we are typing using the power of machine learning. And next, I will talk about communicating with non-textual information, graphics, such as emojis, stickers, and animations, as they play a big part in the online conversation. The core problem of this section is how to support people with various abilities to communicate. In the first section, we talked about text entry, but online communication is not only about text. There are also emojis, stickers, and GIFs, and those information can be very inaccessible for people with disabilities. Let's first talk about emojis. Emoji is our new language. It is also very popular among blind or low vision users. And I'm going to refer to those users as BLV users. According to a research in 2020, over 55% of the BLV users use emojis daily, and even more of them use it every week. But you may ask me, how do they use emojis since they barely see them or they cannot see them? Well, they have a tool called Screen Reader to use a phone. Basically, there will be a focus on the screen and the content will be read out loud. And the user could double tap to select the focused content. And they can also perform a gesture like a swipe to move the focus to another widget. And this is how you navigate through the entire screen by gestures and voice feedback. So how do they use emojis? There is an emoji keyboard which contains all the emojis you can tap. And you can just tap the one you want. So for screen reader users, they will hear all those options one by one using gestures. But the problem is there are just too many emojis. It could take you literally hours to go through all of them. And in fact, we interviewed BLV participants who use emojis, and all of them mentioned that they only frequently using less than 10 emojis because there are too many options. So how could we make the input experience easier for them? Well, researchers showed that BLV users use dictation significantly more than sighted people. We all talk with each other every day, and speech is actually one of the most intuitive ways for communicating. So why can't we speak emojis? And that is voice emoji. It's a voice-based system that supports emoji search, entry, and exploration. So how do we design the voice interaction for emojis? Let's take an example of this one. What will you say to others about this emoji? Well, a robot will say man in lotus position emoji because that's the official name of it. But remember, people talk in descriptively ambiguous way. So there's no fixed way to say this emoji. Maybe you can say the meditation emoji or yoga man emoji or even Buddha emoji. They all make sense. So to enable this natural style of speaking, voice emoji need to locate relevant emojis based on the utterance. To achieve this, we use search engines because an emoji will appear most frequently together with its description. So if we search the description and extract the emojis that appear most in the results, we can find a good candidate. And to help users learn about new emojis, we also added a prediction function inside voice emoji. Whenever you say something, voice emoji will give you some suggestions and you can explore them. In this way, it's more relevant and efficient than just manually going through the whole list. Here is a demo of the system. I need to turn up the volume so that you can hear the feedback. So to search an emoji, you can just say, emoji search, raining day emoji, and then it will return something like this.
Possible emojis are first emoji cloud with rain emoji, second umbrella with raindrops emoji, third emoji sun behind cloud with rain emoji, fourth emoji cloud with snow emoji, fifth thundercloud and rain emoji. More available.
And then you can select the one you want.
Emoji sun behind cloud with rain emoji added emoji sun behind cloud with.
To add emojis directly into the text, you can also say the emoji keyword after the description. For example, if you say the curry rice emoji was delicious, it will return something like this.
The emoji curry and rice emoji was delicious emoji suggestions available.
And there are also relevant emojis suggestions for you. So how will this system perform in practice? We did a study with BOV users from both the United States and China, letting them input emojis with the iOS keyboard and voice emoji. And the average time for finding an input emoji on the keyboard was about a minute, which was pretty slow. And can anyone guess how long it took for voice emoji? Less than 5 seconds, 11 times faster than the keyboard. And the result was consistent across the two languages. And it's not only beneficial on the speed. Participants also enjoy the context-sensitive emoji suggestions. And after using the system for several days, more importantly, the participants felt less isolated communicating with their sighted friends when using emojis. And we just found that the recently released Google Pixel 6 also added an emoji transcription feature, which worked similarly to voice emoji. So the idea of speaking emojis is not only beneficial to BLV users, it can actually benefit a lot of people when they are using dictations. So after I conducted the study of voice emoji, a participant sent me the sticker to say thank you. And I was very surprised. I did not know they also use animated GIFs. So I asked the person how she used it. She told me that her friend sent her this sticker and explained that there's a cat and a heart, and she thought it was cute. But most of the time, when chatting online, she encountered unlabeled GIFs and did not know about their meanings. And the screen reader will just say unlabeled without the description. And that's another barrier for BOV users to engage with the internet culture. But we already know that the computer algorithms are very powerful, and some screen readers can already generate descriptions for static images. So why cannot we generate descriptions for GIFs? Well, it turns out that GIFs are far more complicated than a static picture because they are actually composed of a series of pictures. And this is when I use a Google Cloud Vision service trying to generate a description for the GIF, a cat nodding its head. But the description was completely off, as you can see. And here is a real person's annotation we collected from an online crowdsourcing website. And it's much better. It accurately describes the content, but also point out how you can use a GIF. So there are many challenges to describe a GIF. The first one is the dynamic content. A GIF can include multiple scenes from different sources to tell a story, and that can be hard for the algorithm to connect them logically. Another challenge is many GIFs include cartoon or movie characters, and to make an understandable description, it requires a knowledge of the relevant background information. And lastly, the most difficult part is nuanced emotions expressed in many GIFs. For example, here the man is saying right, but look very reluctant. For now, only humans or who are aware of those meme culture can decipher those subtle expressions. So given those challenges, how can we design a system that provides human-like explanation for GIFs? Well, a simple answer is just use humans, but that can cost a lot of money and energy. A more realistic solution is to combine the power of machine learning with crowdsourcing. We can use a computer vision to provide a fast and rough description, and then use crowdsourced manpower to improve the description quality. And this is what Galley does. It makes machine and crowd workers collaborate to generate GIF annotations. Here is an overview of the system. It has 3 components. A mobile client that is able to recognize GIF contents on the screen and help the user to request GIF annotations. And the requested GIF annotation, GIF, is sent to the server, when the server will perform a visual similarity comparison to check if there's any similar GIF that's already been labeled or not. If no similar GIF is found, it will return an automatically generated description to save the user's time. But at the same time, the GIF will also be posted on the annotation website, where anyone can go and provide their annotations. Once the GIF is annotated, the human annotation will be returned if it's requested again in the future. Let's see a demo of Galley. So this is when the screen reader will say a GIF in Twitter without Galley is on.
Your message, June 20th, 21, attached GIF from you.
There is no description, it just say attached GIF from you. And here is when Galley is on, and it let the user request for an annotation, and now it returns with a human annotation.
Get GIF description button out of list. Last GIF, a brown dog wearing a small hat sits on a chair inside a burning room filled with fire and smoke. It stares blankly ahead and then picks up a mug from the table in front of them and says, "This is fine."
So we invited 12 BOV users to install Galley client on their phones and let them use the system for 3 days. During the time, we act as a crowd worker to provide the annotations for their requests. And they use the system quite often. Turns out over the 3 days, over 500 annotations were requested, which means on average, a BOV user encountered 14 GIFs per day, quite a lot. Although machine-generated annotations was not accurate, participants appreciate how fast the result can be generated. And for human annotations, they were very detailed, of high quality, but some participants complained about the annotation was too long and maybe Galley could have a shorter version available. For emojis, and GIFs, although they are not traditionally text-based languages, people use them every day. And through voice emoji and Galley, I demonstrated how to make them accessible to people with disabilities. We need to listen to the users. Sometimes we need to make use of both machine and manpower to create adaptive and intuitive interfaces. As one of our participants said, it is important to speak the language others are speaking. And finally, after we have all those intelligent input systems, an important question is, how can we evaluate their performance? And in the last section, I'm going to briefly cover 2 model and metrics for text entry system evaluation. In this section, the goal I ask is that how can we objectively evaluate those intelligent text systems with advanced features such as autocorrection? When we have a new feature, how do we know it's good or bad? And in general, we use speed and accuracy as a basic evaluation matrix for text input systems. While the speed is straightforward, the errors are a bit complicated to measure because there are multiple definitions. So to gain a accurate representation of the typing procedure, traditionally researchers use the input stream model to represent the typing process. The model will keep track of what is modified at the end of the text. So in this example, the presented string for the user to type is all roads lead to Rome, and the user actually transcribed all roads lead to Roma. And the input stream will represent that during the typing, the text EED was an error that gets corrected. And the character A at the end is an uncorrected error. So the limitation of this input stream model is that it only allows modification appearing at the end of the text. It could not handle cases where the text is modified in the middle, which means it could not handle modern text entry functions such as autocorrection or copy-paste because they can change the text anywhere. I thus introduced this transcription sequence model that solves the issue by taking snapshots that every time the transcribed text changed. So I also designed a string comparison algorithm that compares the neighboring sequences and reconstructs the whole dynamic process. In this way, the error that happened during the typing process can be calculated. Another problem of measuring the speed and accuracy is that they represent different aspects of the performance. If you have one keyboard with high speed but poor accuracy, and another keyboard with low speed but high accuracy, there's no absolute conclusion on which one is better because we are using two metrics. On the other hand, humans have innate speed accuracy trade-offs. You type faster, you make more errors, and vice versa. So how can we have an overall constant conclusion about the performance? My other project tried to find a performance metric that combines the speed and accuracy information and overcomes the speed accuracy trade-off. This means the metric will show constant scores when the same person types with the same keyboard, even with different speed accuracy conditions. And that metric is called text entry throughput. It is derived from the information theory. We can think of the text entry process as a communication system where the human plus text entry method act as a mid part of the system to transmit the information, and the error act as a noise source in the channel. And from this analogy, we can use the formula to calculate the throughput of the channel, which was originally referred to as the discrete channel with noise by channel. I conducted studies where users typed the keyboards in different speed accuracy conditions and found that among all metrics, throughput was the most stable one. So the goal of my research is to create human-like communication interaction with computers, and touch typing emojis are all part of the goal. But essentially, I want to ask, what is next? We are entering this ubiquitous computing environment where devices are in different shapes with different capabilities. Obviously, we won't carry a keyboard anywhere with us. So how should we communicate with those devices? My vision is to have an input system that is ubiquitous, available anytime and everywhere. I've already started the effort towards that direction, and this project is called Type Anywhere. It enables you to perform query-style typing on any surface with a finger-worn device. Here is a demo of Type Anywhere. I can type on a table surface similar to typing on a keyboard. I can also type on a wall, or I can even type on my laps. Type Anywhere is trained using deep neural network, and it decodes your finger touch sequence into the text. So in that way, you don't need to type each letter precisely, which means as long as you are performing the right finger tapping, you can type the text you want. And in summary, my work uses machine learning and user-centered designs to build better communication experience with computers and to make the digital information more accessible. And I hope that by now, I successfully demonstrated my thesis statement. That is, artificial intelligence can enable and improve advanced text production and accessible interactions with pictures. In addition, new metrics for text entry enable the evaluation of advanced capabilities. Going forward, I would like to explore wider and deeper into the field of human-computer communication. Essentially, I'll be asking 3 questions. What should it be? How can we make it more accessible to everyone? And since we are having those intelligent systems, how do we evaluate their impact on our human and society? The first direction is to ask, what is a communication interaction for new computing platforms? With those ubiquitous computing, we are surrounded by computers everywhere, which means there are many opportunities to utilize the real-world context, such as our locations, our activities, or our interaction with other people. And using this, we can train text systems to provide a more personalized experience based on those real-world context. On the other hand, we can also use more modalities such as gaze, speech, to interact with the device to provide a more natural experience. Imagine a device that can understand your gestures and facial expressions. What will that look like? The second direction is how. How do we design the communication so that the information is accessible to everyone? And by information, I'm not only referring to text or emojis. It can be much more complex than that, such as a shopping website or a mobile application, or using new multimedia formats such as interactive visualization. I believe the way I developed Galley, which is combining the power of machine learning and crowdsourcing, is a very promising way to create accessible interfaces for them. And the third direction is to evaluate the broader impact of those systems, such as their impact on human behaviors and society. One project I've already conducted in this direction is to see how emoji prediction systems change our linguistic style. We made 2 suggestions keyboard, one keyboard that will suggest emojis based on the keyword of the message. For example, if you type game, it will predict game-related emojis. And the other one will suggest emojis based on the semantic meaning of the message, like the lower graphic. And we install those keyboards on people's phones and let them use it for 3 weeks, and to see if the way they compose the message was changed. To our surprise, we found that it was a bit contrary to our intuition. Those suggestion mechanisms did not affect participants' emoji usage. But on the other hand, they did affect their writing style. For example, one participant mentioned that emoji suggestions reflected his message tone, and he would try to modify the tone and see different predictions. In the future, I'd like to collaborate with researchers from the fields of communication and psychology to answer more questions in this direction, like how will suggestion systems influence our language style and our creativity? And how will presentation of the suggestion, how will the presence of suggestion affect the interpersonal relationships? The communication history has evolved for thousands of years, but the human-computer communication is just about to bloom. There are many exciting opportunities to make the interaction natural, humane, and more intelligent, to make the device as our collaborators, our companions, rather than just as a tool. And today I am standing here contributing my part to its evolution. And I hope you can join me together to shape the future of our communication, because of which we exist, we connect, and we progress. Okay, that's all my thesis presentation. But next is your time. I want to say thank you to everyone who helped me to accomplish this dissertation over the years. Okay, this to me is like the most important part. First, I'd like to thank my amazing advisor, Jacob Warburg, my mentors, Alexis Hineker and Shuming Zhai. I couldn't find a clear group photo with Jake, but this looks fun, so I just put it. I was trying to write down some words that would make everyone cry, you know, like words that make people speak at the weddings or like graduation ceremonies. But I found like myself too poor at English, so I would just say whatever comes into my mind. And maybe you can translate them into the crying version in your mind. Jake, I am so lucky to have Jake as my advisor. Well, for now, we are more like friends. Jake told me at our first meeting that at first, you might look me as a great person, knowing everything, wondering if you can ever achieve something as I do. But at the end, you will not even need my help because you're already independent and we can be good friends, but I won't guide you anything on your research. Like after hearing that, I got shocked as a first year PhD because I never thought that the relationship between the student and their mentor could be anywhere close to friendship. You know, it's always like teachers or professors. In my mind, I was always prepared to get the wisdom guides from the master, be obeyed, and just to execute what he says. So interacting with Jake has really not only helped me on my skill training, on my own research, but also shaped what I consider as a good mentorship. Jake told me 3 things that are very important and I still got influenced to today. The first one is ask for forgiveness, don't ask for permission. And the second one is pay attention to details, like tiny details matter. And the last one is be confident at myself. And I'm going to make the same decision again. If I'm, like time can come back to 5 years, I would definitely still choose Jake. Nothing will change. And Alexis is the most supportive person I've ever met at iSchool, or maybe UW, I don't know, like throughout the 5 years. Every word describe her need to add EST ending, like sweetest, kindest, you name it. She almost became my co-advisor at the moment because we have so many side projects and collaborations since year 1. If Jake is the guide of my PhD journey, who trained me to be, like independent, expert, Alexis is the person who opened my eyes to the new world of other areas and show me around and making me appreciate about it. I learned so much about qualitative work and had fun collaborations with her students. And every moment being with Alexis made me feel supported and valued. And for Shuming, I reached out to Shuming like year earlier than I came to UW. During that time, I was a college student, wondering whether I should pursue like further education, like a PhD. I wrote emails asking about my confusion of doing research and asking for advice. And I never thought that our path actually crossed again here. And Shuming is my role model in many aspects, especially in the career and research. And he has put a huge amount of time and energy in fostering young researchers like me. And we had many deep conversations, not only about research, but also about life choices. And he took great care of me during my internship at Google and my fellowship and job applications. So I will be always learning from him. Like even now is my graduation, but I'm still a student. It is my great fortune. It's my great fortune to have my path crossed with those beautiful human beings. And James Fogarty and Leah Finlater, thank you for being my committee members and joining my exams, providing feedback and on my progress and having those conversations. Showing your support is really important, especially like in the later years where I was basically doing the stuff on my own, like in this quarantine time. Although I did not collaborate with you directly, I had a great conversation with your students, and I made great friends with both of your students. And if you got the cake, if you got the cake I sent you this morning, this is the time to enjoy it. To my friends and the Seattle Gang, specifically to Qin Wang, Yiming Zhang, Yuying Liu, Qisheng Li, and Yi Chu, you're my closest friend here at Seattle, and we all go through this PhD hardship together. And so far, no one quits. Yeah, I will leave soon, but it's not quit. Specifically to Yuying Liu and Yi Chu, conversations with you guys made me appreciate the beauty of research, knowing that doing projects is not only for practical or social value, but there is just like this pure beauty of the art and science. And that has definitely refreshed my mind. I met Qisheng in my first iSchool class, and we became good friends since then. I must be so lucky to have someone who is not only a good friend of life, but also can share, like the school struggles and research ideas. And thank you to my friends from college. And here are my dorm mates. I even had a paper published together with Hoen, which is amazing. And friends from high school, and they all helped me a lot after the car accident. And this is like, there is just not enough space for me to put all their faces in one slide. So guess what? I just have more slides. The cheapest thing is in your dissertation talk is that you can put any slide you want. More friends I met when visiting the East Coast, and here is my cat. And talking about gangs, how can I forget the dear I-17 cohort? Hey, sorry about no offense here. I know we are the best cohort ever. Everyone is so supportive. We celebrate birthdays, sending general exam package, and just hung out with gossips about schools and classes. I can just be who I am and share my genuine feelings among you. So thank you a lot. And you might see that Rachel is missing here, but she's here. So everyone is here now. On the right is my 8 lab mates. Those are all the lab mates from 2017 till now, including former members. I learned a lot from everyone. Being with you and having conversation together have never made me lonely. And even in that tiny dark space at MGH 015. Thank you, iSchool staffs, Victor, Wendy, Doug, Dora, Jane, and many other names. I cannot just put all here, but you all helped me navigate through all the school stuff and departmental logistics so smoothly. And special shout out to the IT specialists here, Nick, Nikki, and John, who handled many server and equipment requests from me about my projects. And finally, to my family, my parents and my sister. Family is the deepest root and connection to the world. And it's especially in these 5 years, in a foreign country, far from home, with so much uncertainty happened recently. I want to especially thank my mom. She has accepted whoever I am, supported my decision, every single decision, and pick up every phone call in the early morning when I messed up with the time zone difference. She's the only reason I could make it so far. Okay, more thanks. Here are all my collaborators, including the faculty members from the University of Washington and many other institutions. All the graduate students are shown here and undergraduates I've ever worked with. I'm also very lucky to have collaborated with industrial researchers from internships, so thank you all. And to all of you who joined this dissertation to show support, thank you. All right, at this point, I'm happy to answer any further questions.
Okay, thank you very much, Ray. And thank you to all who have been able